All right. All right. Welcome to the review video for the Intermolecular Forces lecture. This is lecture 23, if you want to refer to that in your notes as well listening to this. So very quickly, I'll just go over what each different type of intermolecular force can be at play in various molecules, and then I'll kind of do a rundown on a way to solve problems that may involve this. So to start off, what are intermolecular forces? To kind of understand the concept, we have to go back a little bit into our electronegativity section when we learned about that. And if you'll recall down there at that periodic table here, that as a rule of thumb, the more right and up you go on the periodic table, the more electronegative an element is. And remember how in a bond, like it shows here with carbon fluoride, that sometimes you get these elements bonded that have vast differences in electronegativity. So for example, here fluorine is a lot more electronegative than carbon. And so we denote that with either this little symbol here, a sigma negative, sigma positive, or this little plus and an arrow to show how one side is more negative and one side is more positive. And so the intermolecular forces deals with this electronegativity concept and how each molecule will react to other molecules in a substance, when they're close together, all kind of chilling together. And basically, the more polar a molecule is, or the more negative and positive regions it has, if it has a super strong positive and super strong negative region, it's going to more strongly attract to others. Whereas if there's a molecule that's kind of even keel all over, then it's not going to be super attractive because it doesn't have a strong positive pole or a strong negative pole. So if we start with our weakest one, London dispersion forces, you can see I even put up top, it's weakest, but everybody's got them. I like to think of it sometimes as friction between molecules. That just kind of helps in my brain when I'm thinking about it. But this shows that even those nonpolar molecules, like I was saying, have a small bit of attraction. There's still, a positive nucleus in the center of each atom and negative electrons around. So even when there's a completely nonpolar molecule passing by another one, even though they're not super strong attraction, there's still electrons that see the neighboring nucleus and vice versa that kind of want to come together and attract each other a little bit. And so this, as you can see here, causes a temporary distribution of electrons. The electrons close to it will kind of push away so that the nucleus can reach out more to the neighboring electrons. And this causes a very temporary polarity when it goes by other molecules. Now, this is not what we'd consider a dipole or permanent in any way. It just happens very briefly as it brushes by a neighboring molecule or a neighboring element, neighboring atom. And so these are constantly changing, shifting these electron clouds to reach out to others. And over here on the right, this is where the idea of thinking as friction can really help. A bigger element or a more spread out molecule here, these polarize and attract easier than a smaller or clumped molecule. So for example, here, this kind of clumpied, it's got a lot of tetrahedral molecularity to it. And so it's kind of this clump of atoms there. It's going to be hard to attract to other clumps and other atoms and molecules going around it because it doesn't have too much surface area. Whereas this molecule here, this big long chain, if you get this long area, it has a lot of space where it could bump into other molecules, other atoms, and form this more attraction. So if you have molecules that have a similar construction of atoms and elements, but one is a lot bigger or one's a lot more spread out, then that one has a little bit more of this dispersion force. It's a little stronger. So then going on to this next force, which is, it's still pretty weak, but it's stronger than a dispersion force, is what we call dipoles. So a dipole, as you can see here, with this hydrogen chloride, is when two atoms are bonded that are not very evenly matched when it comes to electronegativity. And remember that this, let's see if I can go back, when we're comparing it on our table, if the difference is more than 0.4 in their electronegativity, then it's considered a big enough difference that they'll be polar in this manner. And so what this means is that unlike those dispersion forces where this shifting needed to happen to have this temporary dipole, it's already polar. It already has a negative and a positive side to it. And so it is much more likely to attract to those around it, especially when you've got one half of the molecule or one end that is negative and then the other half is positive. That means there's other molecules around it that also have a positive and negative end, so that negative goes to positive and so on and so forth. So that's your dipole attraction. But if you have that's for like pure substances, for example. But if you have, for example, a mixture of one substance that is polar and has dipoles and one substance that isn't, perhaps a pure element or something that's mixed in there, then those pure parts, those pure elements, or those nonpolar molecules will still polarize just like it did with London dispersion and stretch and move its electron clouds a little bit, especially because now they're being pulled by a stronger negative or stronger positive instead of just a neighboring nucleus or electrons. So this one can also happen. It's also stronger than London dispersion, but it only happens for mixtures when you have two different substances. If you have a pure substance and it's nonpolar, it's only going to experience London dispersion. Whereas if you have a pure substance and it's dipolar like this, then it'll be a dipole to dipole interaction. So this one's a little bit weaker, this one's a little bit stronger, but still overall dipole bonds are pretty weak. But if we go to our next one, hydrogen bonds, we're getting to the point where these are pretty strong intermolecular forces and attractions that we're seeing. And what hydrogen bonds basically are, if we start on the right here, they're also a dipole-dipole interaction, but specifically when it involves a hydrogen bond connected to one of these three certain elements, nitrogen, oxygen, or fluorine. And the reason that this is special or extra strong is because these three elements, nitrogen, oxygen, fluorine, as you can see down here, these are super electronegative. They're the top three in the periodic table, basically. And so when they bond with something like a hydrogen that has only one electron, it is covalently bonded, but they're so strong that they're sharing the electron almost 90% of the time. This causes the hydrogen side to be super positive and the other side, whether it be nitrogen, oxygen, or fluoride, to be super negative, just because of this super uneven sharing. So in a normal dipole, you get this partial positive, partial negative. In a hydrogen bond molecule, it has this extreme polarization. It makes it much more attractive to other electrons or other molecules around it, especially if they also have this hydrogen bond. So again, like pure substances like water, these hydrogens, which will be super negative, are going to be very much attracted to neighboring oxygens, which are super positive. And the reason water is a special example of this is because it's a pretty small molecule. It's only got one oxygen and one hydrogen. So basically every part of the molecule itself is an extreme polarization. It's either super positive on the oxygen side or super negative on the oxygen side and super positive on the hydrogen side. So pretty much everywhere a water molecule looks in, a glass of water, there's going to be something to attract it to. So it's got very strong attraction. This gives it the unique characteristics of like strong surface tension. This is why it forms a special structure when it freezes, because it's got these special interactions to those around it. And why it takes so much energy to boil water, because it's got these strong hydrogen bonds. And so these are stronger than dipoles. So far our list it goes from London dispersion is the weakest, and then to dipole and a non-dipole or an induced dipole. And then thirdly, we have our dipole bonded to it or attracted to another dipole. And now we're here at hydrogen bonds, which are pretty darn strong. Next, we have ions. So ions are super strong attraction forces. This takes us way back to when we learned about covalent bonds and ion bonds at the very beginning of class. And if you remember, ions form when certain atoms gain or lose an electron to have a more favorable structure. So I'll just use fluorine again as an example. It's got 7 valence electrons, and it really wants to have 8 because that's more stable for it. So if it can find an electron somewhere to steal from someone, it's going to do it. So it would be a 1 negative charge. And then there various other elements form different ions. And so this, instead of a dipole, where you have kind of this molecule that's, because of how the bonds are, it's attractive on one side or another. You just have this element, this one atom that is super attractive either negatively or positively. So again, we can use fluorine as that example of a 1 negative charge. It's got super negative charge. It's going to want to attract anything that's positive around it. And so if it is in a mixture, if you put a bunch of fluorine ions, I guess, into a mixture of dipoles, similar to here, these dipoles would have, this partially negative, partially positive side. But this fluorine would be super negative, and it'd be attracting all the positive sides to it. And so it's a super strong connection here. It's almost like a dipole on steroids, you could say. And alternatively, whatever element it may be, it could also have a cation, our transition metals form cations, so they'd be much more attractive to the negative sides of polar dipoles. And so those are stronger than hydrogen bonds because they're, hydrogen bonds are like strong dipoles, and ions are like dipoles on steroids, so even stronger than that. And then lastly, the strongest intermolecular force is when you have an ion bonded to an ion or attracted to an ion. And I say bonded because they're so strong, they can be considered as if they're covalently bonded. If you remember that, an ionic bond and a covalent bond, we consider them up there as very similar because they have similar strengths. When you get an anion that has a super negative charge and a cation with a super positive charge, they're going to like each other so much, they're just going to stick together so well and form this new molecule. And so remember, we talked a lot about salt, NaCl, so that's got your sodium elements that are super positive, and then your chlorine elements that are super negative, and they just connect each other really well that they can hold their own structure as a molecule. This here isn't actually NaCl, it's silver chloride, not sodium chloride, but I just thought it was cool to remind us of how that can work. And to tie this a little bit into some of our other lectures with solubility, for example, even though the bond between, this one silver atom and this one chlorine atom, oops, let me go back here, okay. So even if this one silver atom and this one chlorine atom have a super strong force together, stronger than any other dipolar hydrogen bond force it has, it can still dissolve in water because hydrogen bonds can be, can stack up on a multiple different elements here. So let's take this chlorine atom, for example, it's got a pretty big surface. It's a big element. It's bigger than, than silver, obviously, and a lot of others. And so if you get a bunch of water molecules around this chlorine atom is going to be super negative, and so it's going to attract all of the positive hydrogen atoms that are around it. And so instead of having just one chlorine atom, you'd end up having multiple, dozens, however many can fit, honestly, of these hydrogen or these water molecules attaching to it on the hydrogen side. If you get enough of those, this chlorine atom is eventually going to say, well, I'm not going to stick around with this silver anion anymore, or the cation, because I'm getting more attraction, more friendship, so to say, than from all these water molecules. And so it'll split apart. And at the same time, all the negative oxygen sides of the water molecules are surrounding the silver cation, and so it's getting pulled away as well. And so that's how things like this can dissolve in water or other strongly hydrogen bonded liquids, is because it can kind of surround these different elements and give it enough attraction and love that it leaves its partner, so to say. All right, so now this part about how we're going to solve problems when it comes to, a test, because that's what we're all reviewing for. That's what we want to do well on. So remember in lecture, Dr. Mortensen gave us a few steps to help us in solving these things. So I kind of took some of that and kind of what I figured out while I was doing assignments and figured out what worked. And so that's what I'm going to share with you today. So first, we kind of start with what he gave us to do. Usually they just tell you a molecule or a structure. You have pure water, or you have this, whatever formula. What's the strongest intermolecular force it can have in here? So the first thing you want to do is just draw a Lewis structure. So for example, down here, if they give you acetic acid, you can draw out its Lewis structure just so you can visualize a little bit better what elements are involved, what kind of bonds are going on, this and that. And then secondly, you want to determine the molecular shape. And so the reason this plays a role is that if it's a wonky shaped, an asymmetrical molecule, then it's going to be pretty hard for it to be nonpolar, if that makes sense. So like this molecule, for example, you can see like one half of it's got carbon and a bunch of hydrogens, the other half's got an oxygen and a hydrogen, so it's not symmetrical at all. And so the only reason this would be a nonpolar molecule is if every single bond itself was nonpolar. And so that having the molecular shape kind of gives you a preview of what the polarity of this molecule might be. And then thirdly, is you find your polarity, if any, with your partial charges or ionic charges, if you know about that. And so you'd go through each bond and you just determine what are the polarities of this. So remember, to do that, you just kind of got to keep in mind with your electronegativity and your periodic table, like if you have a sulfur bonded to whatever this is, or I'll just say chromium. Or no, I won't say that. I'll say a fluorine and a boron. I don't know if they'd even bond or if they like each other, but we know that fluorine is super electronegative, and boron, even if it is electronegative quite a bit, it's not as much as fluorine. So therefore we'd have a polarity with fluorine on the negative side. And so going back to our example here, acetic acid, we know that carbon and hydrogen bonds, they are nonpolar. They fall within that 0.4 and under difference. And so they're nonpolar. But if we look at this oxygen and carbon and this oxygen and hydrogen, we know that oxygen is super electronegative. And so it is a polar bond, especially here with the oxygen and hydrogen. So we know that we've got this asymmetrical molecule. We've got some polarity in the charges. So now let's kind of break it down and see where we're lying in what forces are at work here. So what I do is I go through the list. I Sometimes if I try and think and just pinpoint which one's the strongest, I can miss something. But if I just start at the top of my list from London dispersions to dipole-induced dipole, dipole-dipole, hydrogen, ionic dipole, and ion-ion, if I just go through each one of those, we can find out which ones are involved. So let's start here. London dispersion forces. The easy answer is yes. Everyone has London dispersion forces, no matter what kind of molecule it is. I kind of think of that every molecule wants a friend. And so it's got at least a little bit of attraction to those around it. So yes, we've got London dispersion forces. Let's go to the next one, dipole and induced dipole. Well, we know that this is a nonpolar molecule. And in this question, let's say that it was pure acetic acid. That way we know that there's no other molecule in here. There's no other substance in here to be nonpolar and therefore induce a dipole. So we can kind of rule that out as there's no dipole-induced dipole. But since we know that it's got polarity, it's got some parts that are negative, some parts that are positive, we know that this molecule itself has some polarity. It can be considered a dipole. And so in a pure substance with itself, yes, there will be some dipole to dipole interaction. So we can kind of check that off as yes, we also have that one. Next, we have our hydrogen bonds. And remember those three elements I told you about, nitrogen, oxygen, and fluorine. If we have any of those bonded to a hydrogen in our molecule, we can consider it has hydrogen bonds. So we can see here, we do have an oxygen bonded to our hydrogen. Therefore, we can say this is available for hydrogen bonding. This hydrogen here would be super positive in its charge, and so surrounding acetic acid molecules, like ones with this oxygen chilling out here, which would be super negative, they'd be attracted together a little more strongly than a normal dipole would be. So again, we can check that. Hydrogen bonds are good. And lastly, ions. Is this an ion at all? Now, this one is kind of tricky when I picked it. You'll remember on our polyatomic ion chart that we've been memorizing in class, that acetate is a ion. It's got a negative charge. But this is not acetate, it's acetic acid. It's got this extra hydrogen bonded to it. So as a whole, it's not an ion. These are covalently bonded. It's not an ionic bond at all. So this doesn't really have, even though it would be an ion if it was acetate, in its current form as acetic acid, it is not an ion, and therefore we can kind of disregard that when it doesn't have an ion to the dipole or ion-ion attraction at all. So then if you look through again back at your list of what you've done, we checked off London dispersion, we checked off dipole to dipole, and we checked off hydrogen bond. And you can see the furthest down we got, or the strongest we got, was hydrogen bond. And so we can kind of determine that the strongest force going on here is our hydrogen bonding. And then sometimes a question may ask how this relates to relative strength or macroscopic properties. They might give you a second formula and say which one has a stronger force. So say we did have acetate in it and said, what's this one? This one we'd get all the way to ions. It has an ionic charge, and it has an ionic charge, and so we could say it is stronger in its intermolecular forces than acetic acid is. But also macroscopic properties, it can say things like which one of these has a higher boiling point, which one of these are, let's try to say, which of these has greater surface tension, for example, things like that. And the main rule is that, the stronger the intermolecular forces, the more the molecules want to stay together. They don't want to be separated from each other. So boiling, for example, if they have super strong intermolecular forces, it's not going to want to separate and go into gas and liquid and go away. They want to stay together. So if it has super strong forces, it's not going to boil very well or very easily. Take a lot of energy. And so that is how you determine your intermolecular forces. And that is how you can use it in problems to determine which ones are stronger than other molecules, or which bonds are stronger than other bonds and attractions. and how you can relate it to macroscopic properties. Good luck on the test. You'll do great.